Well, this is the hands-on part of the tutorial. So if you go to the folder 224, in the part of calibration, you will find the notebook of the tutorial, which I have it open here already, but as you will see, it's exactly the same. So let's proceed with that. This is the table of contents of the hands-on tutorial. We first have an introduction where we will see which data we're using and also the models we are going to be analyzing. Then we will be measuring the calibration of the models, both expected calibration error and also visualizing reliability plots for a deeper understanding. And then we will see a couple of techniques for improving model calibration during training and post-training as well. So let's start with the introduction. This first part is not worth mentioning. It's just preparing the column to be able to use it. So this first part, you should be able to execute it without any problem. And once we are finished with preparing the collab, here we will be start working with the data. We will be using this collection of images, which is the MinTs, and it's prepared for both retina and derma. But for this hands-on tutorial, we'll be using derma. Here you can then change to retina for trying another data set. Also, it's important to say that I have already executed everything, so we will not be going cell to cell because some of these cells take time, but you should also be able to execute it without any problems. So let's prepare the data loaders. This is how we split the train, validation, and test for both data sets, depends on which one we chose. And then here is how it's divided. The 7,000 for train, 1,000 for validation, and 2,000 for testing. And this is how the classes are distributed. We can see that there's some imbalance between the classes, but this is how the data set is divided. And here we can see how the images we are working with look. So next, this is also the hyperparameters that are fixed depending on which of the data sets we are using. So for the model, we will be in this first part working with let's call it a simple model, and also the same model but with a version of it being overfitted. So we can compare the different metrics for both models. So one is trained during 5 epochs and the other one is trained during 20 for the case of the derma. So those are loaded, the dictionaries, and it's also important that to know that this is a folder that is related to this column, so on which the trainings are already done. And also there's a file called utils where a lot of the functions being used are implemented here. So then let's do the inference for both models. And we can see that for the simple model, the training AUC is a little bit higher than the validation AUC, which makes sense. But the difference is not that big. And then for the overfit model, we can see that for the training AUC, it's way bigger in comparison to the simple model than the validation set. So then let's plot the probabilities, and also we can see that in the overfit model the probabilities tend to be higher, like all of them are more put in the values close to 1 than in the simple model. So measuring calibration. Let's go compute the confidence expected calibration error. This concept is explained in the theoretical part of the tutorial, but basically it's the mismatch between the accuracy and the confidences computed for the model. So for the simple model, the EC is 0.05, and for the overfit model, the EC is 0.12. So it's way bigger. And than the simple model, which makes sense because the expected calibration error gives information about the mismatch between the probability and the accuracy, meaning that for the overfit model, the mismatch would be greater since the confidences will be way higher in this model than in the overfit one. However, we cannot know whether this is overfitted or underfitted just with the expected calibration error metric. So we will go see some reliability plots. So when plotting these reliability plots, we see that in the left that we have this simple model versus the right that we have the overfit, the gap between the diagonal, which is the perfectly calibrated model, and the accuracy, they are way bigger in the overfit model than in the simple model. In the simple model, the points of the accuracy are way closer to the diagonal. And also we can see that the EC it's smaller for the simple model, as we already saw, and also the negative log likelihood. Then let's go see a couple of ways on how to improve this model calibration. Here, something I forgot to say is that in the overfit model, we can see also that the probabilities need to be reduced in order to be in the diagonal. So this is how we know that this model is overfit and not underfitted. Okay, so for improving model calibration, we will be seeing post-training technique, which is the temperature scaling, and a training time calibration technique, which is the level smoothing. So the temperature scaling basically is a technique to improve calibration without modifying the model predictions. No, we just optimize in a validation set a single scalar parameter. Then this parameter is used to temper the predictions of the network in the plus of max logic space. So when the temperature is greater than 1, scaling reduces the logic of the magnitude, meaning that the model is less overconfident, and this is reduced. When the temperature is smaller than 1, the opposite happens. The model is underfitted, and with the temperature, we increase the probabilities. So in here, we're just collecting all the logics of the validation set. And in here, this is the function used to find the optimal scalar call temperature. And here we can see how the temperature goes changing during this optimization of the parameter, and here how the negative log likelihood reduces until it cannot be reduced anymore. So here we see that the temperature is way bigger than 1, meaning that this is overconfident. So let's see how this applies to the EC. So when computing the EC, after using the temperature scaling, we can see that it is reduced until from 0.1 to 0.03, which is a big amount to be reduced. So in the reliability plots, on the left we have the reliability diagram of the overfit model, and on the right the same model after using this temperature scaling. So we can see that the EC is way lower. Also, the negative log likelihood is reduced, and all the accuracy points are almost in the diagonal, which is shows a really good calibrated model. So then another technique for improving this expected to improving the calibration of a model during training, it's the level smoothing. So the level smoothing is a regularization mechanism that try to be effective against the overconfidence. However, it goes at the risk of overfitting. So here we load this level smoothing model, and we compare it to the other models, the simple model, the overfit model that we already saw, and also the level smoothing model. In here, we can see that the metrics are really similar to the simple model, which gives us a good idea that maybe the model is better calibrated. Here we plot the probabilities, and we see that for this is the simple model, the overfit model, and on the right, the level smoothing model. And we can see that this is clearly weird because the probabilities are distributed in a very different way than in the other model. So let's see what is happening. The ECE, as we already saw, these two, for the overfit one is bigger, but also we can see that the level smoothing, even if the metrics for the training were similar to the simple model, the ECE is way higher even than the overfit model. So let's see the reliability plots, and we can see that for the accuracy points, they are above the diagonal, but way above. So we can see that for the reliability diagram on the right, this is super underconfident. So we should use temperature scaling or other techniques to be able to reduce this gap between the accuracy and the confidence produced by the model.